Okay, this video goes with the 6.1 notes on Polygon angle sum theorems. So first we're going to look at the some of the stuff on the Savvas site. So for the Explorer and the Reason, it says use the tool to draw a pentagon. So let's do that. Pentagon has 5 sides: 1 side, 2 sides, 3 sides, 4 sides, 5 sides. That's more or less of a traditional pentagon. We can also, grab some of the vertices and move it around. This is what we would call a convex pentagon. Here is an example of what we would call a concave pentagon. If I can imagine 2 points inside a polygon and connect those together with a segment, let's say a point there and a point over here, if I can connect them together so that this segment goes outside the polygon, then we have what we call a concave polygon. Another way of looking at this is to think about this angle right here where the convex place is. This is an angle bigger than 180 degrees. 180 degrees would be straight out through here. Let's do a ray. So if I did a ray here, this would be 180 degrees of angle, and we can see that looks like maybe we have like another 60 degrees here, so this is more like 240 degrees. That's another way that we can check for a convex polygon, or concave polygon rather, is if you have one angle inside that's bigger than 180 degrees. Okay, so most of what we're going to be dealing with are the convex polygons. And it says draw a line that includes the sides. So we're going to pick, say, this angle down here. I'm going to draw a pair of lines that go with the sides of this polygon. So we're talking about this angle right here. Now notice that you have this interior angle, which is some number of degrees. And then by vertical angles, this outside angle here is also congruent to this interior angle at this vertex. And then you have these other, this pair of angles here, they're actually supplementary to the interior angle. Like this angle here is a linear pair. It's an exterior angle. It's a linear pair with this interior angle of the polygon. Together these make 180 degrees. And then by vertical angles, this angle here is also the same as this exterior angle in terms of the degrees. So we have 2 pairs of angles formed at each vertex with the sides of the angle of the polygon. 2 of the angles are congruent because those are equivalent to the interior angle, and 2 of those angles are congruent because those are equivalent to the exterior angle, and together they're supplementary. The interior angle and the exterior angle is supplementary. Going this way, interior and exterior angle are supplementary. So let's look at the notes page now. So it says for part A, choose one pair of lines that intersect at a vertex. Is each of the 4 angles formed at the vertex an interior angle or exterior angle of the pentagon? Okay, that's what we're trying to show. Looking at this vertex here at the top of this pentagon, these 2 are interior angle equivalents. These 2 are exterior. Now this is the actual interior angle. These are both exterior angles. This is a vertical angle with the interior angle, so it's the same measure. And both of these exterior angles are the same measure. And then together, the interior and exterior pairs are all linear pairs, which means they all are supplementary and add to 180 degrees. Part B, are the relationships the same for the angles formed by the other pairs of intersecting lines? Yes, at each one of these angles, each one of these vertices, the same relationship exists. You've got basically a pair of interior angles and a pair of exterior angles in terms of their measures. Part C, if you drew a hexagon and the lines that included the sides, would the relationship between the angles at each vertex be the same as the pentagon? Yes, they would. Let's go back and look at that and see. So let's draw a hexagon now. So let me get rid of this. Now we're going to draw a hexagon. So a hexagon has 6 sides. 1, 2, 3, 4, 5, 6. So there we have a hexagon. I can like stretch it out and make it look more like you might be used to seeing in terms of a hexagon. Again, this is a convex hexagon. If I was to do this would still be a hexagon because it has 6 sides, but this would be what we would call a concave hexagon. And notice here, you've got an angle, interior angle that's bigger than 180 degrees. That's the sign of a concave polygon. Also, you could think of a pair of points someplace inside the polygon where if you connect them together, that segment actually goes outside the polygon to get to the other side. That's the other test for a concave polygon. So with this hexagon, what they're hoping that we see here is that at every one of these vertices, let's go this way, the same relationship exists. You've got an interior angle, an equivalent vertical angle, and then you've got an exterior angle that's supplementary to that interior angle, and the other vertical angle is also the exterior angle. So we got the same relationship. Linear pair, linear pair, linear pair, linear pair. Interior, exterior, exterior, interior, interior, exterior, exterior, interior. Okay, let's go back to the student companion. So the relationships basically stays the same. It doesn't matter about the number of sides. At each vertex, you've got a pair of interior and a pair of exterior angle measures. Let's move up. Okay, so example 1, to try it, explore polygon interior angle sums. So we're talking about a convex octagon. Let me go to this example here. I think we're on example 2 though. Let's see what this is. Okay, here's our big question. How's the number of sides of a convex polygon N relate to the sum of the measures of its interior angles? Well, let's look here. Here we have a triangle. It's got 3 sides, and we know that a triangle has 180 interior degree angles measures. So 3 sides adds up to 180 degrees. If we go to 4 sides, a quadrilateral, we can actually break that into 2 triangles. Now each one of these triangles has 180 degrees worth of angle measure. We have 2 triangles, which is 2 less than the number of sides. We've got a 4-sided figure. We get n minus 2 is 2. 2 times 180 gives us 360 degrees for the interior angle sums in a hexagon, or in a quadrilateral. If we go to 5 sides of pentagon, we can see that 5 take away 2 is 3. We can construct 3 triangles, and each one of these triangles has 180 degrees worth of measure. Altogether, that gives us 540 interior degrees for hexagon. Now this example is talking about an octagon, which is an 8-sided figure. We can count 1, 2, 3, 4, 5, 6 triangles. N take away 2, 8 take away 2 is 6. We have 6 triangles. Each one of these triangles is 180 degrees. That gives us 1,080 degrees worth of interior angle measures if we were to add up all the angles inside this octagon. So let's go back to the student companion. Okay, so how many triangles are formed by drawn diagonals in a convex octagon? 6. N take away 2, 8 take away 2. And what's the interior angle sum for a convex octagon? It's going to be 6 times 180. The number of sides, take away 2 times 180, is going to give us the interior angle degrees. So we get 1,080 for an octagon. Let's move up. Okay, let's do example 2. What's the interior angle sum of a 17-sided polygon? So if n is 17, n take away 2 is 15. So 15 times 180 is going to give us 1800 plus another 900. 2700 degrees is going to be the sum for the interior angles of a 17-sided polygon. For part B, we're talking about a regular polygon. Now, in a regular polygon, all the sides are congruent and all the interior angles are congruent. So if we were to think about this 17-gon here, there would actually be 17 congruent angles that would have to make up this 2700 degrees. So if we wanted to see if this was a regular 17-gon, we would have 17 equal angles that made the 2700. We could do 2700 divided by 17. Well, now we'd probably end up with a decimal, but 2700 divided by 17 would be what each one of those 17 angles measured. But that only works if it's regular. Otherwise, we would just have to add up all the angles and make sure that the sums came out to be 2700 degrees. So that's what we're getting at in part B here. Each angle of a regular polygon, or n-gon, measures 172.8. How many sides does the polygon have, or n-gon have? So here's our formula for the measure of a regular interior angle in a regular polygon. N take away 2 times 180 is the total number of degrees, and n in the denominator is the number of angles we actually have. So we have 2 less than the sides number of triangles at 180 degrees apiece, and we have actually the number of sides worth of vertices that we can divide by to see what each one measures. So where you need to solve this for n. So 172.8 is equal to n minus 2 times 180 over n. Multiply both sides by n, and then use the distributive property. We get this. We're going to take 172.8 n away from both sides and add 360 to both sides. So these kind of swap places. And we end up with 7.2 n is equal to 360, which gives us 50. So a 50-sided polygon, a 50-gon, if it's regular, each angle inside that 50-gon, each one of those 50 interior angles measures 172.8 degrees. Altogether, they measure whatever 48 times 180 is, but because there are 50 of them, we would divide by 50, and when we do that, it should come out to be that each one is 172.8 degrees. Okay, let's move on. Example 3, with the exterior angle measures of a polygon. So let's look at the Savvas example 3 site and see if they have some help on this. So here's their example 3. So here we have a, let's see how many sides, 1, 2, 3, 4, 5, 6, 7. Here we have an octagon. It's a convex polygon. It looks like it's regular, but they're not telling us that it's regular. But if we look at each side here, if we were to extend the sides sort of like in a pinhole pattern here, we can see that each one of these interior angles has an exterior angle pair that makes 180 degrees. So whatever this interior angle is, this exterior angle at that vertex is supplementary to it. Each one of these angles, if you just go in one direction as you go around. We also, we'll see that on another one, saying we could do this one here and get angle 2, but maybe we might want to go this way and talk about angle 4 right here, which is the same thing. But generally in a pinhole pattern, as you go around one at each vertex, these exterior angles are all going to add to 360 degrees. So this is what they're going to try to show us down here. So this is sort of like an algebraic type argument for it. The sum of the exterior angle measures is equal to the sum of the interior and the exterior, which are 180 degrees each. So we've got an 8-sided figure. There's 8 sets of 180 degree angles if we include the interior and exterior angle at each one. Like this 5 in the inside angle there, 6 the inside angle there, and so on as you go around. Now the interior angle sums, though, if we use the formula 180 times n take away 2, that gives the number of inside angles. So if we took the total amount of angles, angle pairs, subtract the interior angle parts, it should leave us with what these exterior angles add up to. And when we do the math with that, use distributive property here and everything, and simplify, we end up with the sum of the exterior angle measures is 360 degrees. So this is an algebraic argument basically telling us that these exterior angles, one at each vertex, all add up to 360 degrees. And it doesn't matter about the number of sides of the polygon. If this was a square, we'd have the same situation. We'd have 4 angles. Each one of those exterior angles would be a 90. Each interior angle would be a 90. We'd have 4 sets of 90s representing the exterior angles, which would be 360 degrees. So the sum of the exterior angles of any convex polygon is 360 degrees. So the sum of the exterior angle measures of a convex 17gon, the number of sides doesn't matter. Exterior angles always going to add up to 360 degrees. So we take the total number of degrees, 17 sides. We've got 1780 degree interior-exterior pairs there. And we take away the interior angle measures, which is the n minus 2 times 180 part. Basically, we're left with 2 times 180, which is 360. Let's look at example 4. Suppose that these 1, 3, 4, and 6 are congruent to each other, and that 2 and 5 are congruent. And that also we can think about 3 as being the same thing as angle 2 plus 30 degrees. And they want us to find basically the measure of these angles. They want us to find the measure of angle 4. So if we line them all up, all of these angles, 1 plus 2 plus 3 plus 4 plus 5 plus 6, need to add up to 360 because we're talking about exterior angles here, one at each vertex. 4 of them are the same, so I'm just going to call those x's. And then the angle 2 that's congruent to angle 2 and angle 5 are congruent to each other. So I just basically call those both angle 2 because they're both the same thing. And then over here, we can use what else they tell us about. Angle 3 is equal to angle 2 plus 30. Well, if we want to solve that for angle 2, angle 3 take away 30 is going to be angle 2. So down here, I'm going to substitute angle 3 take away 30 for these 2 measures of angle 2. We got 2 measures of angle 2. Each one of those is angle 3 take away 30, and angle 3 is x. So each one of those is x take away 30. When we simplify, we end up with 6x's take away 60 is 360. That leaves x being equal to 70. So the, x is equal to 70, and x is basically what we let each one of these missing angles represent. And angle 4 is x, which is 70 degrees. Example 5, find the measures of the interior angles. The measure of each interior angle of a regular 100gon is 3x plus 26.4. So we've got 2 different ways of dealing with this. We've got the 100gon, which is n is 100. So 100 take away 2 times 180 is going to give us the total number of degrees. 98 times 180 is that total number of inside degrees. It's regular, though, and it's talking about each angle. So we can divide by 100. This is going to give us the measure of each one of those 100 congruent angles. And they're telling us that that came out equal to 3x plus 26.4. So I'm setting 98 times 180 divided by 100 equal to 3x plus 26.4. What did we do here? I simplified on this side. This came out to be 17,640 divided by 100. So I moved the decimal 2 places and made that 176.4. So this simplifies to 176.4, and that's equal to 3x plus 26.4. Take away 26.4 from both sides, 3x is 150, x is equal to 50. So for that to work out, x has to be 50. Let's look at these do you know hows. So if we use this polygon, one handy way we have of counting polygons is to kind of mark your starting place and go either clockwise or counterclockwise. So if I mark this, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 9-sided polygon. We call that a nonagon. 10-sided would be decagon. 11 undeca. 12 dodeca. Bigger than that, we just do 13gon. And octa is 8. Hepta is 7. Hexa is 6. Penta is 5. But for our purposes right now, this is a nonagon, a 9-sided polygon. It's convex. So look at number 5. What's the sum of the measures of the inside angles? Well, the number of sides is 9. 9 take away 2 times 180 is going to give us the interior sums, which is 7 times 180, 7 times 100, 700, 7 times 80 is 560, 1260 total number of degrees. So all these angles inside have to add up to 1260 degrees. What's the sum of the measures of the exterior angles? If we were to extend this out and think about one at each vertex, or do the, whatever the linear pairs are here, these exterior angles are always going to add up to 360 degrees, regardless of the number of sides. Okay, number 7 is a heptagon. It's got 7 sides. 1, 2, 3, 4, 5, 6, 7. So y in is 7 for this one. 7 take away 2 is 5. 5 times 180 is going to give us 900, which is what the total number of degrees add up to. If we add up the numbers that were given and subtract from 900, we need 100 more degrees to make 900. So 100 must be what y is. And then x is the external angle at that vertex. These are a linear pair. These have to add up to 180. So x has to be 80. Number 9, what are the measures of the exterior angles of the polygon shown? So first of all, it's a 1, 2, 3, 4. It's a pentagon. The easiest way to do this would be to, since it's a pentagon, we know that these inside angles have to add up to 3 times 180, which is 540 degrees. And if we add up all the x's and simplify, we end up with 13 x's plus 20 is equal to the 540. Take away 20 from both sides, divide by 13, we get x is equal to 40. So x is equal to 40. Now if x is equal to 40, that makes this 130 degrees, which leaves this exterior angle to be 50. If we let x be 40 here, 160 take away 10 is 150. That exterior angle is going to be 30. Here we have 55 degrees. So the exterior angle needs to make 180. That's going to be 125. Here we have 3 40s. It's 120. That leaves 60 for the exterior angle. And here we have 85 degrees. It takes another 95 to make 180. So altogether, these angles add up to 360 degrees. So get 10. The sum of the interior angles of a regular angon is 6,120. What's the measure of each interior angle? Now they're talking about each angle, and it's a regular. So that's going to be our n minus 2 times 180 divided by n formula. And the total number of degrees they're telling us it's 6120. That's n minus 2 times 180. When we divide by n, we would get each degree. So when we simplify that, let's see what we got. This derivative property here, well, we can actually solve for n. N is going to come out to be 36. So I solved it for n, add 360 both sides, divide by 180, and it comes out that n is equal to 36. So this is a 36gon. Now, since it's regular, each angle is going to be congruent. There's going to be 36 of them. 6120 divided by 36 comes out to be the measure of each interior angle. So if you want full credit for this, you need to figure out what 6120 divided by 36 comes out to be.